wait 30 more seconds. Huh?
I think we're ready whenever, Tim.
I'll wait 30 more seconds.
Okay.
That's right, yeah. Hey, 2:30. Hello and welcome everyone. It is my great pleasure to introduce today Clark Zimmerman, who is a third-year PhD student with us, graduate student, hopefully soon to be PhD student, sorry, not jumping the gun. And Clark will tell us today about the AMOC. Just as a means of introduction, Clark came to us from Boulder, Colorado, and I've learned that many have followed that trajectory in this department, so well trodden, with a background in physics, and has been working with me and also Liz on the stability of the Atlantic Meridional overturning circulation. This is Clark's AP presentation, and the paper was published earlier this week, so it's nicely timed. And
everyone go look at it so I can get more
hits. Well, I was just told by Anchor that Anchor, our unofficial Blue Sky liaison, posted it on Blue Sky, which is much cooler than X, and it's gotten some traction there. So, let's go Blue Sky. All right, please take it away, Clark.
All right, can everyone hear me okay with this? Okay, awesome. So thanks for that wonderful introduction. So my name is, in fact, Clark. And I will be telling you some insights into AMOC stability today, specifically sharing some of the results from my recent publication titled Slowed Response, Not a Robust Signal to Collapse. This publication would not have been possible without my co-authors, Till and Liz in the room, and Dylan McNamara at UNC Wilmington as well. So just to orient ourselves a little, our agenda for the day is going to be a lot of background, just to make sure we're all on the same page. So starting with some AMOC background, going into some CSD background, and then I'll introduce the box model used in the study, I'll show some results, and then I'll go into some future directions I might take while here at this department. So we're going to get started with the AMOC background, and let me introduce my PowerPoint helper, Mate. So please direct your attention to wherever her cute little face is on the slide, and that will help you follow along with my talk today. So what is the AMOC and why do we want to study it? Well, the AMOC is an incredibly important element of the global climate system. It's responsible for transporting heat from the tropics to the higher latitudes in the northern hemisphere, as Mate exhibits. Additionally, North Atlantic deepwater masses aid in the regulation of global climate by sequestering excess heat and CO2 into the deep ocean. Okay. And while the primary drivers of the AMOC is debated, the strength of the AMOC is generally considered to be proportional proportional to the density gradient in the Atlantic Ocean, specifically between the subpolar North Atlantic and the South Atlantic. Sorry. Her face is not in the right spot, so just imagine that it's slightly in a different spot. So anyway, it follows that an increase in the buoyancy of the water masses in the subpolar North Atlantic region is generally assumed to lead to a weakening of the AMOC. So some contenders for AMOC drivers are the deep convection in the subpolar North Atlantic region pushing the circulation forwards, or alternatively, the strong westerlies in the Southern Ocean pulling the circulation through Ekman upwelling and Ekman transport. So the focus of this talk is not AMOC drivers, however, but rather the existence of an alternate mode of this circulation. So it's been posited that the AMOC is bistable with an on or strong state, like the modern AMOC, and an off or weakened state, like during previous ice ages. In fact, some have argued that the Donskoy-Oshkosh events of the past glacial period can be attributed to state changes of the AMOC. And a great and 100% realistic example of what the world would be like if the AMOC shut down would be the Hollywood film Day After Tomorrow, where, spoiler alert, the entire northern hemisphere freezes over. That was sarcasm, by the way. Okay, so the possibility of a shutdown of the AMOC is hotly debated, and it's yet unclear if the modern day AMOC is even bistable, so if there is an accessible alternate steady state in our modern world. Additionally, there has been much conversation regarding the current trajectory of the AMOC in observations, and just last week, a paper by Terhar, Vaught, and Foucault found that the AMOC may not even be weakening based on observations, as has been claimed in the past. So, what might cause a collapse of the AMOC if such a thing were possible? To understand one potential mechanism, let's take a look at the AMOC from a few different perspectives. So first, here you can see a depth latitude schematic of the AMOC, and this is how cross-sections of the AMOC are typically displayed. However, the second plot depicts AMOC in density space, and this better illustrates how the density of AMOC water masses increase as they move north before any actual deep convection occurs. And the third plot, we can see density in depth space. This highlights the shoaling of dense water mass classes that occur in the subpolar regions, with more stratification in the northern hemisphere due to the lack of Ekman pumping here. Okay. So now let's zoom out to the surface and subsurface currents associated with the AMOC in the subpolar North Atlantic. Be sure to follow Monte along here because I'll be jumping around the slide a bit. So this region is very important to AMOC dynamics due to the North Atlantic deep water formation that occurs here. The water masses that are brought up from the subtropics by the North Atlantic current, which is the red arrows on this plot, undergo water mass transformation, increasing their density classes to form North Atlantic deep water before sinking and being transported southward at depth. Sorry, all of these animations are in the wrong spots. But you can imagine that the densification occurs here, there's some deep convection, and then it travels along one of the isopycnals before shoaling again in the south. Okay. So if you want to learn more about this water mass transformation, you should talk to Tedra. But for the purpose of this talk, I simply wish to introduce one potential mechanism for an AMOC collapse. So if the AMOC is driven by this deep convection, which is debatable as I mentioned, then an increase in buoyancy in this region could trigger a potentially catastrophic positive feedback, potentially resulting in a sudden collapse of the circulation. This feedback is known as the salt advection feedback, in which increased stratification and thus decreased convection in the subpolar North Atlantic reduce the northward flow of high salinity surface waters, further decreasing convection and thus AMOC strength. However, incredibly important to this water mass transformation, and as a result the AMOC, is the subpolar gyre. So it's highlighted here with the orange circle, which is actually approximately in the right spot this time. And I'll get into the importance of this ocean feature a little later on, but you can imagine that a vigorous mixing by a wind-driven circulation could mitigate some of the impacts of the buoyancy-driven positive feedback I just described. So this brings us to our first half of our science questions for today. First of all, a lot of recent papers have predicted or attempted to predict a collapse of the AMOC through either modeling studies or observations, which begs the question, is the modern AMOC even a bistable system to begin with in our global warming world? Secondly, Chen and Tong released a paper in 2023 criticizing some of these collapse papers due to a lack of data of observations or certain biases in the observations. So that brings up the question if we even can assess the AMOC's dynamical stability using our current modeling and observational techniques. And thirdly, many simple idealized models of the AMOC can readily simulate a collapse, but comprehensive models typically do not. Comprehensive models such as like CESM or large global climate models. And so I wonder why this might be the case. Why idealized AMOC models simulate this when comprehensive ones do not. But in order to answer these questions, we need some way to assess dynamical stability. So get excited. Here's the mathy part of the talk. So if you don't like math, like close your eyes maybe. Before we can talk about what CSD is, we need to understand what a critical transition is. So simply put, when gradual changes in forcing lead to sudden, irreversible changes in the steady state of a system, that is a critical transition. So here we can see a system described by this differential equation. It has a bistable regime. It's bounded by two saddle nodes that are illustrated with stars here. And as the system is forced linearly with some forcing, F on our x-axis here, it evolves from the monostable regime at the tail into the bistable regime in the middle. A critical transition occurs when the system experiences a sudden, irreversible transition from that bistable regime into the alternate monostable regime. Note, the state variable could be anything from the stock price to temperature to an ecosystem's productivity, but during this talk we're going to be referring to this x state variable as the AMOC stream function or maximum stream function. And the forcing could also be any number of things, but we'll be discussing freshwater forcing today. But before we do that, let's explore irreversibility a little deeper. This is most easily done from a potential well perspective. The wells, or potential landscapes shown around this plot, indicate the system's preferred state, or states, on the x-axis for some given forcing. Anywhere on the potential landscape where you have a zero slope or a flat line, that is a steady state. When that location is also a local minima, we say that state is stable. When it is a local maxima, it is unstable. For example, if we just look at this transect in the bistable region, the upper branch solution corresponds to the right-hand well, or that local minima. The unstable solution corresponds to the local maxima in the middle, and the lower branch solution to the left-hand well. So if our system starts out in the upper branch, or in the right-hand well, as the forcing is ramped forward, the system would fall from the right-hand well into the left-hand well. However, if we reverse the ramping, as the system would require a lower level of forcing before the right-hand well is again accessible. This is referred to as irreversibility because it leads to a hysteresis in the system. So, can such a critical transition be predicted using statistical indicators? That's the idea behind critical slowing down theory. So when applying statistical indicators, I'm referring to applications to the stochastic noise of the system. They cannot be applied to a deterministic system. We need that stochastic noise to see the shape of our potential landscape. So we can think of that noise as kicking the ball, which is our system, and seeing how it moves differently given different shapes of the potential well. So when there's a narrow well, as in the tails of this plot, the ball would move really randomly, which can be depicted as a low variance and a low autocorrelation. As it moves into the bistable regime with a wider well and it loses some stability, deviations grow, as does the memory of the system due to a decreased restoring rate. And these changes are manifest as increasing variance and increasing autocorrelation, or so-called early warning signals. And this is still not making any sense. That's fine. I'm going to show a quick example. And since it is an AMOC talk, might as well show an overturning circulation example. So this is the two-box model from Chessy in 1994. It was adapted from the Stommel 1961 box model. This model is super simple. There's only two boxes. One is warm and salty, one is cold and fresh. The temperatures are clamped, and the salinity is forced, with the subpolar box getting progressively fresh. And here the state variable is the salinity difference between the two boxes. That can be understood as the strength of the density-driven overturning Q. So here we can see a single stochastic run. Ignore the plot that's underneath it. We can see a single stochastic run or realization of thermohaline flow from the Chessy two-box model with freshwater forcing and sphere jumps on the x-axis and salinity difference between the two boxes on the y-axis. In this model, the apparent saddle node bifurcations are very robust. And again, the state variable is salinity difference, so a small difference represents a strong overturning, and a large difference represents a weak or shutdown overturning. So the trajectory of this single realization mostly follows the analytic solution, with some randomness associated with the noise, resulting in a transition just past the critical thresholds, or a lower saddle node. In order to analyze the statistics of a model, we generally want to conduct many realizations, or many runs, so we can analyze 100 or even 1,000 realizations to better understand the overall behavior of the model. So to that end, we can now see 5 realizations of thermohaline flow, showing that when the model is run with linearly ramped freshwater forcing, as well as stochastic noise, it experiences a range of critical transitions all around the critical threshold. If we look at the associated potential wells at 3 different locations in our time series, we can see how the state of the system goes from being corralled by the tight well on the left, to having large fluctuations in the bistable regime, to falling off the cliff into the alternate steady state on the right-hand side. I said right at first, it starts on the left, ends up on the right. Okay, as expected by CSD theory, the variance and Lagrange autocorrelation both increase as the system approaches the critical threshold. As you can see in this simple example, with a robust bifurcation, CSD theory holds up well. If we only had access to that single run I showed first, you would be able to use these changes in variance autocorrelation as an early warning signal of the critical transition that we see. Okay, armed with our understanding of how CSD theory is supposed to work, we can take a look at the second half of our science questions for today. So, through the years, many different indicators have been proposed to be used as early warning signals, starting with just using variance, to just using autocorrelation, to using them both together, to using different, slightly modified parameters. That leads me to the question of if any of our current CSD indicators are robust early warning signals of critical transitions, meaning that they could be applied to any situation and we could trust the results it gives us. Secondly, a paper by Till and Ian Eisman back in 2015 came out about how these indicators can trigger a false alarm when applied to Arctic sea ice. So that begs the question, in what physical scenarios might CSD indicators trigger this type of false alarm? And lastly, a recent paper by Chapman, Sinet, and Ritchie in 2024 studied how using different calibrations of the same model could lead to different tipping mechanisms. And that leads me to wonder if the reliability of CSD indicators also depends on model complexity and background climate. And now, these are very broad, generic questions that are not specific to the field of oceanography or climate science, but since this is an AOS seminar, not a math seminar, we'll be discussing them all in the context of the AMOC, more specifically in the context of an idealized box model representing the AMOC. So with that, let's introduce the box model being used in the study, starting with a 5-box formulation. This was developed by Wood et al. In 2019. This model is similar to the Chessy 2-box model, but it has some added complexity. So shown here are the 5 boxes. We have a North Atlantic box, Atlantic thermocline box, Indo-Pacific thermocline box, Southern Ocean box, and deep water box. The model includes a fully Atlantic cold water path. It also includes a warm water path through the Indo-Pacific thermocline by way of the Drake Passage. Okay, I'm going to give you a second to kind of look at this geographic portrayal, because when I go to the next slide, we're going to look at some equations and some less clear pictures to those who are geographically minded. So I'll give you a second to sit with this. Okay, enough with that. Now we're going to go do some math. Okay, so we can see the 5 boxes now in a non-geographical orientation. Oh my god, all of my animations are fudged up. It's fine, just pretend you can't see any oranges or any Fs. So in this non-geographical orientation, we can see the saltwater pathways in between each of the boxes. So Q here is the salinity transport strength of the AMOC itself, and the arrows illustrate the saltwater pathways, so you can follow Mate as she goes through the trajectory. This is for an on circulation. If Q crosses 0, the arrows would switch directions, and thus the circulation would go to the opposite direction. Okay. In addition to the salt transport via the AMOC, there is additional transport via upper ocean gyre circulation, representing the subpolar North Atlantic gyre, or KN, the South Atlantic gyre, KS, and the South Pacific gyre, KIP, as well as diffusion in between the bottom and Southern Ocean boxes, or the deep and Southern Ocean boxes, sorry. And lastly, there's salt exchange between the atmosphere and the ocean. These are denoted by FX. They are representing evaporation and precipitation. And the sum of all the F terms is 0, so we can maintain that salt conservation. So the model itself is a set of two sets of 5 ODEs that represent the salinities in each of the boxes for both forward and reversed overturning. I'm just showing the forward equations here. So as you can see, the equations are quite simple. They're just linearly exchanging salt across the pathways I just described as a function of the salinity difference between the boxes that are connected. And these equations can be calibrated to a climate model or theoretically to observations as well. But from here, I'm going to be discussing them as calibrated to the pre-industrial or one-time CO2 control run of the intermediate complexity Earth system model, famous B, following from Wood et al. 2019. But before going into any results, I'm going to introduce the 3-box formulation of the same model. So this was developed by Alkiuen et al. In 2019. It is dynamically the same as the 5-box. Sorry. It's dynamically the same as the 5-box model, but it's easier to deal with analytically. So when the 5-box model is run for large ranges of hosing, which I will talk about in a second, the salinities of the southern and deep boxes change very minimally. As a result, Alkiuen et al. Decided to hold these salinities constant at their initial values. When we do that, the ODE for the north box remains unchanged, and the equations for the Atlantic thermocline box now just includes an SS naught constant rather than the variable SS. Additionally, since there's now only 3 adjustable salinities, the salinity for the Indo-Pacific box can be solved using salinity conservation, giving us a very simple 2x2 ODE model. Now, salinity itself is not very interesting. We care way more about the strength of the AMOC, so we need some way to calculate that strength. Recalling what I said earlier on, the strength of the AMOC can theoretically be determined by the density gradient between the subpolar North Atlantic and the Southern Ocean. In order to calculate this gradient, we can get salinity by integrating our system of ODEs. And we now have an equation for AMOC strength that can be solved for any value of Sn. Notice this is where the nonlinearities in our model originate. If we were to plug this equation into a dsn dt equation, then we get an Sn squared term. This nonlinearity gives rise to rich dynamical behavior in this model, including bistability and multiple types of bifurcations. I'll discuss some of these features here. If you're curious about those features that I do not discuss, please find me later, because I would love to talk about them. Okay, and most of the results I show today will be from that 3-box formulation, but I would also like to introduce this 2-box reduction of the same model that I developed. So some of the rich dynamical behavior I just mentioned that occurs in the 3 and 5-box formulations is super interesting, but it kind of complicates the story at times. So I further reduced the model, removing the extraneous behaviors, but maintaining similar dynamics, namely the saddle node bifurcations that we care about, in order to ensure robust findings in this study. So this 2-box reduction fixes the salinity of the Indo-Pacific box to its initial value, and the ODE updating north box remains unchanged. Now the Atlantic thermocline is updated through salinity conservation, so the model is now just described by a single set of ODEs, and we can still calculate Q in the same way. Okay, up till now I have only discussed the state variable Q, but that's only half the story. So next I'm going to describe the forcing that we apply to the model. So a 2020 paper by Kalin Jansen explores the role of the Clausius-Clapeyron relation on the AMOC in a warming climate. In this experiment, the hydrological cycle is enhanced to the degree that would occur if the globe was warmed by 2 Kelvin, according to the Clausius-Clapeyron relations. Shown here is the isopically averaged meridional overturning stream function and zonally averaged potential density for the control simulation on top, with a difference in the stream function between the plus 2K equivalent and the control on the bottom. So psi, or the stream function of the AMOC, increases throughout most of the Atlantic, and North Atlantic deep water formation moves southward as a consequence of the salt advection feedback I mentioned earlier. So this study finds that in relation to our modern climate, an enhancement of the global water exchange with the atmosphere serves to strengthen and deepen overturning on the mean, unlike Stommel's 1961 findings. These conflicting results motivate further research into potential shutdown mechanisms of the AMOC, if it is in fact bistable. And on top of an enhancement of the global water cycle, global warming induces melt of the Greenland ice sheet, which is another source of fresh water into this subpolar North Atlantic region. just to note, neither Stommel nor Kaelin Jansen nor myself directly account for increases in ocean temperature due to global warming, focusing only on the salinity component. Of course, in the real world, the AMOC would not experience only one or the other in isolation. So the work I discussed today is purely theoretical and serves to challenge the notion of CSD theory rather than attempt to predict the true trajectory of the AMOC. That being said, let's incorporate how we incorporate this global warming signal into the box model. So in order to represent the hydrological cycle, an increase in the hydrological cycle associated with warming plus an increase in Greenland melt, we introduce a slowly varying forcing variable, H. I will use the terms hosing and freshwater forcing interchangeably. They both refer to H. So we introduce this hosing into our air-sea flux terms. So shown here is how we would add it to the salinity equation for the north box, where A is what proportion of the freshwater is hosed into each box. So the sum of all the A terms is again 0 to maintain that salinity conservation. So, as I mentioned before, we can only look at the statistics of a model if it has stochastics. So our H is not purely deterministic. We need some noise to analyze. So the hosing is comprised of both a deterministic and stochastic component. The stochastic component represents natural variability in surface freshwater fluxes. It's mathematically defined as fast time-scale white noise, where here sigma is 0.9 sphere drops, and N naught represents random sampling from a Gaussian distribution of mean 0. Sigma was chosen such that the resulting Q time series have comparable variance to observations of AMOC maximum stream function. And the deterministic component is the slowly varying global warming induced hosing, and it ranges from -0.5 to 0.5 sphere drops. Now, in order to apply CSD to any time series, a few conditions need to be met. Firstly, we need to have a separation of timescales. So our H bar and H prime must be on sufficiently distinct timescales. Secondly, we need to maintain a near equilibrium approximation. So the state variable must be in or close to its steady state. CSD is not applicable to systems in transient states far from their steady state. And thirdly, we need a robust signal. So this just means we need sufficient data, both in terms of length of time series and density. In order to maintain these conditions, our deterministic hosing varies incredibly slowly, increasing at dH bar dt of 5 times 10 to the -5 sphere drips per year. This slow ramping of H bar allows the CSD indicators to be calculated under the assumption that the transient equilibrium of the system remains close to the stable equilibrium. Real-world increases in freshwater forcing under global warming may be faster. This calls into question whether condition 2 is satisfied in like observational time series, for example. However, relating box model parameters to the real AMOC is very complicated. The moral of the story is our simulations are set up such that all 3 of these conditions are held, because we're primarily concerned with how CSD performs if all 3 conditions are met. Okay. I know you've all been waiting with bated breath for the most exciting part of the presentation, so let's get to some results. So here we have the analytic solution for overturning transport strength Q under freshwater hosing H. For one calibration of the 3-box model with stable solutions as the solid black and unstable solutions dashed. Like before, the saddle node bifurcations are shown as stars. Additionally shown here is this delta H term. So this is the width of the bistable regime for the analytic solution. It's described as the range of hosing over which 2 or more solutions exist. Mathematically, we can calculate it by taking the H at which the upper saddle node exists minus the H at which the lower saddle node exists. Simply the length in units of hosing of the bistable solution. So while the 3-box model can exhibit bistability in the AMOC, as shown here, the existence of these saddle node bifurcations in the model are not robust, unlike the Chessy model shown earlier. In this model, I will show how the width of the bistable regime, delta H, is actually a function of the gyre transport strengths Kn and Ks. In other words, the existence and size of a bistable regime for the AMOC is dependent on how vigorously the Atlantic gyres mix salt in between different water masses. So let me orient you to this parameter space first. The x and y axes are the transport strengths of the subpolar North Atlantic gyre and which exchanges salt between the North Atlantic and Atlantic thermocline boxes, and the South Atlantic gyre, which exchanges salt between the Atlantic thermocline and southern boxes. The shading indicates the width of the bistable regime, delta H. As I discussed on the previous slide, delta H is clearly dependent on the strength of these gyres, and it ranges from more than one sphere drips all the way to 0. The thick dashed line here separates our parameter regimes, where the color proportion shows the bistable regime, where the salinity bifurcations exist, and the white section is the monostable regime, where there are no local bifurcations. Today, I'm going to show you integrations of the 3-box model in each regime with stochastic fluctuations, and we'll calculate the statistics of each to see if the CST indicators can help us identify the difference between these two parameter regimes. The first model run I will discuss is with small gyre transport strengths, shown as the pink star in this plot. Afterwards, I will discuss a monostable run using gyre strengths indicated by the blue star. So let's dive right in. So when we integrate this model forwards with stochastic fluctuations in the bifurcation regime using small gyre transport values, we can see both noise and bifurcation-induced tipping from the on state into the reverse state, as the analytic solution would suggest. If we reduce the hosing from the collapse state, we would see a hysteresis in Q. Thus, the transition here is irreversible. Let's consider some statistical indicators now. I will show the evolutions of the variance and 2 autocorrelation parameters of the model AMOC over time. If CST theory holds, we should expect to see an increase in all 3 indicators in this regime. Well, all 3 do increase, so that is great. In this regime, CST theory succeeds in allowing us to accurately predict the upcoming critical transition from a stochastic time series. Now, let's consider a model run in the no bifurcation regime, or the monostable regime. We can see that the system moves continuously along the analytic pathways with no sudden transitions. So in this world, the linear gyre-based salinity exchange mediates the nonlinear salt advection feedback. So this results in an AMOC with a single fixed point. Now, with an AMOC with a single fixed point, how do these statistics look? If CST theory holds, we should expect to see no notable increase in any of the indicators. Well, it appears that all 3 indicators again increase as the hosing increases, despite the lack of a critical transition. This raises a false alarm. So in this regime, CST theory fails without knowledge of the underlying system, analyzing a stochastic time series, and the indicators it produces. One might be prompted to anticipate the approach of a critical threshold that does not exist. And these results are robust when the same experiment is conducted using the 2-box formulation. So we have an accurate early warning with the weak gyre exchange and a false alarm with the strong gyre exchange. And these results show how CST indicators behave qualitatively the same for the bistable regime and the monostable regime, but this raises the question of whether, or more generally, there's any distinguishing features in the variance and autocorrelation between bistable and monostable regimes in this model. So let's examine it. So this plot is similar to the parameter space plots from before, but now the colors are the regressions of variance and autocorrelation on hosing, so the slopes of the plots I showed on the previous slide. If CST theory were functioning appropriately, we would expect the hashed areas to look distinct in some way from the colored areas, specifically featuring neutral or negative slopes. However, for every combination of gyre transport strengths, the calculated indicators warn of an approaching critical transition. This is manifest by the robust positive slopes throughout these plots. Neither indicator's parameter space shows any mark of the split between the bistable and monostable regimes. This is evidenced by the dashed curve, which indicates that demarcation between those 2 regimes. and it does not correlate with any of the contour lines of the CST indicators. In conclusion, there is no clear method to distinguish between a false alarm and a true warning by CST indicators without additional insights into the system's dynamics. Now, you may be thinking, okay, well, in both cases you showed the AMOCs did shut down in terms of Q crossing 0. Is that what the indicators were showing? Well, no. The indicators do not inform us about the physical properties of a system, only its statistical properties. As such, the indicators are warning us of the salt ejection feedback, which does exist in all the tested regimes. It's simply not strong enough to cause a critical transition in those which contain sufficiently strong linear mechanisms, in this case the gyres. To illustrate this point further, we can readily conceive of a scenario where changes to the physical system result in rising CST indicators without a shutdown of the AMOC. This is illustrated with a simulation where we fix the hosing to 0 and instead gradually reduce the North Atlantic gyre transport strength. Here, the response to perturbation slows and CST indicators do increase, while Q still remains far from 0, even in the unrealistic yet technically physical limit of the gyre shutting off completely. So this response to increasing gyre-based salinity transport can be understood by considering the disparity between overturning timescales, which is on the order of 100 years, and wind forcing timescales, which are on the order of 1 year. Thus, when overturning drives salinity exchange, the time series are highly autocorrelated. So when wind-driven circulation strengthens, autocorrelation is reduced, as the salinity can equilibrate more quickly. Therefore, as the ratio of overturning to gyre exchange is increased by reducing Kn, the response time of Q increases as well, even without an impending shutdown or collapse. Thus, a slowed response is not necessarily critical. So all the results I have provided thus far illustrate the need to understand the dynamical landscape of a system before confidently applying CSD, which begs the question, do we understand the AMOC's dynamical landscape? Not really. We know that an idealized box model is not a comprehensive representation of the AMOC, and even in this simple model, the demarcation between the bi and monostable regimes is sensitive to different model formulations and parameters, and the values for gyre transport strengths are quite sensitive to the model calibration as well, and are incredibly difficult to diagnose in the real world. So here we can see the same delta H parameter space from before, but with some additions. Scattered across the parameter space are the gyre transport strengths diagnosed from several Earth system models, and these values vary widely across different models of similar complexity. They vary even more when we consider estimations from more comprehensive models and observations. All these open questions lead me to some future directions I hope to take with my work. So firstly, while the 3 and 5 box configurations are dynamically similar, the increased complexity in the 5 box model appears to have a predominantly stabilizing effect on the system. The width of the bistable region decreases for most of the KN-KS parameter space when going from 3 to 5 boxes, although this is not ubiquitous. For a range of smaller values of KN and KS, the 3-box configuration actually has a smaller delta H. And the differences between the green and purple regions on this plot is an area I'm interested in exploring more thoroughly. Additionally, the 5-box model is monostable over a larger region of the parameter space. That's the area between these two curves. So the gyre transport strengths, which result in a bifurcation for the 3-box formulation, do not necessarily result in a bifurcation of a just slightly modified formulation of the same model. This is to say that there are values of transport strengths where simulations using 3 boxes result in abrupt collapse, while simulations using the 5-box remain stable. This highlights the dependence of stability on model complexity, and it's consistent with previous studies that have found lower order models to feature more bistability than higher order models. However, the reasoning behind this phenomena is not yet well understood. Okay, as I mentioned at the beginning, while the hosing is meant to represent changes in the water cycle associated with global warming, this model doesn't actually include any warming. So to test how the background climate impacts the degree of bistability, we consider the 3-box configuration as calibrated to a 2-time CO2 run of famous B, rather than the pi control or 1-time CO2 run that we investigated throughout the presentation. This allows us to compare AMOC stability in two climate states, pre-industrial and global warming. The dashed lines on this plot, or the dashed line on this plot, is the demarcation line for the pi control case, while the dotted line is the demarcation line for the 2 times CO2 case. In the global warming scenario, the delta H parameter space contains a larger monostable or white regime than the pre-industrial scenario. Additionally, unlike when comparing the different model configurations, for all gyre transport strengths tested where bistability was present, the pre-industrial simulations feature a larger delta H than the matching global warming simulations, shown by this plot being entirely green. Furthermore, global warming simulations with a weak North Atlantic gyre transport give substantially smaller delta H. This suggests that in a warmer background climate, the AMOC steady state may be more stable and less likely to feature critical transition under hosing than in a colder climate. This also raises the possibility that as the background climate warms, the AMOC could transition from a multistable attractor to a single attractor without crossing any sort of bifurcation or critical transition. This highlights the difficulty of assessing the dynamical stability of a complex system in a climate that is changing in a multitude of interconnected ways. So to summarize my future directions, I wish to explore the questions brought about by the last 2 results I just showed, starting with how model complexity might influence the stability properties of the AMOC. To that end, I wish to continue the development of a model hierarchy of increasingly complex AMOC models to see how the stability properties change in each formulation. Secondly, I'd like to learn more about or study more about how we can assess the stability of the AMOC if it is in a transient rather than steady state. To that end, I would like to continue my work with my collaborator Dylan McNamara into attractor reconstruction techniques, which can be applied to systems that are not in or close to a quasi-steady state. Lastly, in addition to the questions, an additional question raised by this research that I did not touch on during today's presentation regarding different types of bifurcations. I'm curious if different types of bifurcations result in differences in the stability of a system, and following that, if there's certain stability assessment techniques that work better if it's, say, a local bifurcation versus a global bifurcation, or if there's any that work equally well for all, like a universal early warning would be cool. But that brings us to the end of this talk. Thank you all. Special shout outs to my advisor Till for being awesome, my GAC Liz and Dan also for being awesome, my co-authors Dylan, Liz, and Till for also being awesome, and my Muay Thai family at Ford Thai Boxing for keeping me sane. Probably would not be here if it was not for punching things every day. My friends here at AOS for letting me complain to them when my research isn't going well. Also thanks to my family and, most importantly, Mate. I expect to hear lots of ahs throughout the room. Aww. Oh, she's so cute. Wow. This is her writing my AP questions for me. Don't tell my committee. Wow, so cute. Okay, now I can open up the floor to questions.
Thank you, Clark. Well, questions. Before we start questions, I do want to warn you about Clark's punching abilities, so be careful in what you ask. Grad students, maybe first. Yes, Jack.
So you talked about like one of the future directions you wanted to take this was kind of looking at, you know, like more in complex models.
Mm-hmm.
I guess my question is, what goes into, how do you build up a more complex model? Do you plan to add just more kind of regions to that? Do you add more variables to that? And where do you kind of think there would be like a level of like diminishing marginal returns almost as to like
Right.
what's worth it to add and what else do you hope to get out of that?
Exactly. So that is another question of like, what do we even mean by complexity? Does that just mean degrees of freedom? Does that mean like different types of interactions? So there's a couple different models that I'm working on now. One which makes the, it's basically the 5-box model, but it makes the temperature a free parameter for all the temperatures of all the boxes. That adds another set of free variables. Another option would be to add more diffusivity into the model, which wouldn't add any more free parameters, but it would add more interactions between the parameters. Another option, thanks to Dave Bonin for this idea, is letting the volumes of the boxes change as a function of the Q, because we can imagine those water masses wouldn't stay the exact same size if Q is going weaker or stronger. So like, there's many different ways, and after doing those 3 experiments, I kind of want to look at what I find before just keep adding more random stuff, maybe do different combinations of those things, just to see if, like, because I really want to understand what is it about these higher complexity models that causes increases in stability. Is it the diffusion? Is it the free parameters? We don't really know, we just see this trend, so I want to kind of pick it apart as much as possible to figure out like what the actual mechanism is.
I have just a super quick clarification, and I might have missed this, but your parameter space, you're looking at the gyre strength in those 2 regions.
Yes.
And you showed a bunch of types of models where you have the actual gyre strength. Do you also have the observed, like what we currently observe for the gyre
Yeah,
strength
so
in those
it
regions?
is really freaking hard to get the actual observations, because if you just like stick a velocity measurement tube into the water, like how are you gonna say like, oh, that's the AMOC that's pushing that versus that's the gyre that's pushing that? So like there are some estimations out there, but I couldn't find like any 2 that agreed with each other.
Okay.
So very difficult to diagnose.
Do you at least have like a range? Because your parameter space went up to like 50.
Right, which like I feel like 50 is probably unrealistic. Like when I tried to figure out the gyre strengths from CSM, I think I got something like 10 to 12 sphere drips. So I couldn't tell you exactly, but yeah, 50 is probably more than it would be, 0 is probably less than it would be.
Matt?
Maybe it's not important, but I'm curious about the effect of ice, annual ice on and then off. That in the fall, wouldn't that cause a tendency to spin up and just for increasing salinity, brine rejection, and then freshening in the spring? And then maybe that would also be an annual cycle in temperature forcing as well that would be in phase with that. Is that an important thing to consider?
Oh, that's very interesting. That's another way I could increase the complexity of this model, because right now my time step is 1 year. So the seasonal cycle is not super relevant to the way that I'm integrating the model. If I was to shorten the time step to be, semi-annual or something that involves the seasons, then that would definitely be something I need to consider.
Or justify random forcing that way.
Right. Yeah.
Yeah, Clark, maybe it's a follow-up to Matt's question, and it's an ignorant question, but I'll say it anyway. Can you line up your potential complexities and then just plug them into the model and test them one at a time? Is there anything valuable that comes out of that, as opposed to trying to throw all of the complexity at it at once as you build complexity? So I don't know how to say it better than that. I hope that's understandable, but the idea being, if you use the simplest construction, but you use it to test one after another various mechanisms, is that also a way to
Yes, that would
add
be
complexity?
like. Do you mean like adding complexity to the 2-box model instead of adding it to the 5-box?
Exactly.
It's already complex.
Yeah, because is it easier to
that is
interpret what you
interesting.
get?
Probably would be, and that is interesting. Yeah, maybe I would consider just adding them straight to the 2 or the. I think the 3-box model is just like significantly more physically realistic than the 2-box model, because in order to make those reductions, like, well, we get the same dynamics, it's no longer like really the same model at that point. So I would probably, if I wanted to test that, I'd probably try adding them to the 3-box model. But that is interesting, and it would be interesting to see the difference between like adding diffusivity to the 3-box versus adding diffusivity to the 5-box to see if those changes are different.
It might be easier to interpret. And if you can, if you have a sense of what your foundational complexity model is, and you just kind of said it, 3 is better than 2, and not maybe so much better than 5 isn't so much better than 3. Maybe that's the way to test it.
Right. Yeah, it's a great idea.
Okay.
Thank you.
Yeah.
I guess maybe taking a different look at that, it seems to me that the 2 metrics that you're looking at, the variance of the system and then the autocorrelation, are related through like a fluctuation dissipation relationship, where the covariance matrix, the variance of the system itself, or the variance of the system is determined based on the dynamics, which are trying to squish it to no variance, like
Yeah.
trying to stable dynamics.
Yeah, the return rate.
Yeah, versus that input of variance from some sort of stochastic process.
Mhm.
And it seems like you might be able to address these your enhanced complexity by relating those dynamics to the structure of the potential well that you're putting
Absolutely.
in there. And then rather than having to worry about case studies of complexity, you could say something more general about the kinds of structures that would generate a CSD-like response in the absence of bistable equilibrium.
Absolutely. So in my exploration into complexity, which I have already started, I'm exploring this type of relation between the stability, which is the slope of the potential well, and the resilience, which is the distance between my stable equilibrium and the closest unstable equilibrium. So literally diagnosing the shape of the potential landscape to see how that changes with the different model formulations. So I'm not sure if that's exactly what you were asking, but that is, like, as I'm exploring this complexity, I'm more interested in the shape of the potential landscape in the phase space rather than just calculating the variance and autocorrelation.
Right, and what I'm thinking is that if the shape of that, right, the restoring force of that has something to do with the d by d, the gradient of the potential well there.
Exactly.
So if you have like a dynamical system that's a flat region in there, then that restoring force is weak, which enhances the autocovariance as
Yeah,
well.
so the stability is that restoring rate.
Okay.
Because it's per year, so it's the amount that it restores to its stable state per year, essentially.
Okay.
Yeah.
So that in the center of where you're at gives you some idea of the autocorrelation.
Exactly.
Got
You
it.
can calculate the autocorrelation and the variance if you know sigma from this value.
Okay.
Yeah.
I'll ask a question. Let's say we had a climate denier who looked at your results and said, okay, maybe this says that we shouldn't believe any of this research is coming out because you've just shown that the CSD framework basically doesn't hold up in the simplest of frameworks possible. Why should we believe any of these big papers that show that there might be an AMOC collapse under the, coming, or an AMOC slowdown? How would you respond to that kind of person interpreting your work?
I would say, you know what, some of the things you're saying are true, in that we shouldn't just blindly trust these CSD papers that use this as the AMOC's definitely going to collapse in 2025, which is 2025 now, so we'll see. But that doesn't mean that we should just keep burning fossil fuels and testing our luck. We should continue researching to fully understand these physical systems, because as scientists, that's our job, is to understand the physical systems around us. And we shouldn't just try to publish in order to make splashy headlines. We should focus on making good science, but that doesn't mean that global warming is good. This doesn't mean that it's impossible that the AMOC would collapse. It just means that we need to be more careful before we're using these types of techniques.
Anchor.
I just have a curiosity question, which you may not have a good answer to, but is all salinity the same? As in, like, salts are overriding chemicals. I'm just kind of curious about, whether there's differences in densities or different things that, could explain some differences in dynamics of salt transport.
I have no
Just
idea.
kinda curious,
That's very interesting. Yeah, I know, I've taken one chemistry class in my life, and it was in high school. So I could not tell you the answer to that.
I don't think it would matter.
Reading the book on salt right now.
Yeah.
It's
Just
similar
exactly that.
across the ocean, even the salaries are different, just like any other type of salt. It's quite well mixed.
Yeah, that makes sense.
I mean, it's super important for the ecosystem, right?
Yes.
And
Yeah, that's
the
usually-
biogeochemical.
That's what my head lives.
Well, maybe she
Right,
could
exactly.
on another planet with
So
different.
you
Yeah,
know,
there
you don't want to just pour an ACL in the North Atlantic to keep it to keep it going, because you don't know what you're going to do to the trophic network.
Yeah, can you do this in a rotating tank? Can you somehow collapse?
I think
We should totally
the
do
two-box
that.
model, Stommel's original 1961 paper, was all experimental. It was not a theory paper. So the two-box model is absolutely something that can be done experimentally.
He just imagines that it's a thought experiment, no?
No, he does it.
Does
He
he
has
do
like
it?
2 boxes and there's like a tube between them and like some other crap. Yeah.
But no, I think that's a great idea. Yeah, let's do some.
Don't need to rotate it.
Don't even need to rotate it. I mean, if you want the gyres, right? Anything else? Yes.
Question, I just have an announcement.
Yes.
Which is, this is hot off the press, but the next 4 departmental seminars are now all scheduled for our faculty candidates as of an hour ago. And so please come to the next, come to all the department seminars, but the next 4 are particularly important as they are our candidates and guests who will be presenting for this faculty position that we're hiring next year for this Rise Earth initiative. So just wanted to pass that word on, since you all here for seminar, this means that I assume that you'd like to come to this time.
Yeah, feel free to vote for me also. I could become a professor.
All right, let's thank Clark once more. Thank you.